So, as we said in the first lesson, one of the basic requirements of the k-means algorithm is that we specify the number of clusters we want to obtain. Now, there are situations in which we know ex ante, so before starting our analysis, we know clearly how many clusters we want to obtain. If you remember the example we considered at the end of the first lesson, we wanted to to cluster our observations into two groups, defaulted and non-defaulted. So the number of clusters was there, it was 2. Now, imagine that this is not the case. Imagine that we don't know how many clusters we want to obtain. That is to say, we don't have a strong belief for what concerns the optimal number of groups our algorithm should identify. What can we do? Now, we will see in the next classes that, at least according to me, it is better to use other techniques, like, for example, hierarchical clustering. But there are still some techniques that can be applied in the k-means situation and that are more or less pseudo-objective. What do I mean with pseudo-objective? These are techniques that rely on quantities that we obtain from the algorithm, quantities like the inertia, that we will use in order to find what is the optimal number of groups that minimizes or maximizes some of these quantities. And those quantities coming from data can be assumed to be somehow objective. I prefer to say pseudo-objective because in any case you will see very often it's up to you to decide if k, the number of groups, is 2 or 3, it's 5 or 7, because these techniques can give very similar results for different numbers of k, and at the end of the day it's always your decision. The first technique that we consider together in order to identify the optimal number of clusters starting from the data, so when we don't have any a priori about the number of clusters we want to obtain, is the so-called elbow method, which is based on a quantity called inertia. Now, the inertia is nothing more than the within cluster sum of squares. How it is computed? It is very simple. Imagine that we have run an algorithm, our k-means algorithm, with a fixed k, let's say k equal to 3. Now, what happens? We can, for every single observation I, from 1 up to n, where n is the number of observations in our sample, we can compute the quantity di. Di is nothing more than the distance of our observation from the center of the cluster, from the centroid of the cluster to which it belongs. Now, once we have computed this di for every single observation, we just take the squares of all the different di's and we sum them. This is nothing more than the within cluster sum of squares, also known as inertia. The inertia is the basic ingredients of the elbow method. How does it work? Now, imagine that we run the k-means algorithm for different values of k. So we can start in principle with k equal to 1. It means that all the observations belong to just one class. K equal to 2, two groups. 3, 4, 5, 6, 7, 8, up to the limit, if you want, in which k is equal to n, the number of observations. In that specific situation, you will have that every single cluster will contain one observation, which is also the centroid, because the clusters coincide with the observations. Now, a very simple thing to understand here is that if you increase the number of clusters, the inertia will tend to decrease. Why? Because if I consider 3 clusters, I will have to compute the distances of every single points from the corresponding centroid take the sum of the squares, and that will be my inertia for the case k equal to 3. But if I have 10 centroids, if I have 20 centroids, you can imagine that the distance of every single observation from its own centroid, so from the center of the cluster it belongs to, will tend to decrease because now we have a lot of points in our space. And in the limit, when we have as many centroids as observations, then the distance will be zero. So if we build a plot in which on the y-axis we have the inertia corresponding to the different case, and on the x-axis we actually have the case, so the number of clusters that we are using in our k-means algorithm, we can expect to observe a curve that decreases in the number of case. Now, in the elbow method, as the names suggest, we look for the point in this curve, which is a decreasing point, in which we observe an elbow. And the point here will more or less correspond to the optimal k. Now, in many situations, it is actually the case in which it is very simple to observe the elbow. And so identifying k should not be a great problem. In other situations, conversely, it can be a little bit more subtle because we may have that maybe the elbow is either k equal to 4 or k equal to 5 because they are quite close in the shape of the elbow, as we will see in an example with R. Now, what happens once we have identified the elbow, which is at the end nothing more than the number of clusters such that we observe the greatest decrease in the inertia, and such that after that number, the decrease in the inertia that nevertheless will always happen, it's smaller and smaller and smaller. So once we have identified the optimal k, then we're done. So that will be the number of clusters that our algorithm better defines, and our job will be, for example, to give an interpretation to the clusters. Again, in my view, as a subjectivist, it is always better to have an a priori about the optimal number of clusters. Otherwise, I would suggest using other techniques, as we shall see in the next classes. But for sure, the inertia is a simple way of having at least a first idea of the number of clusters we can expect from our data. Consider the plot on your screen. This plot is based on the data that we have used in the first lesson to study defaulted and non-defaulted customers. So what I have done, I have computed the inertia using the k-means algorithm for my observation, dividing the observations in one cluster, two clusters, three clusters, and so on. What you can see is that the biggest decrease in the inertia is when we move from one cluster, so all the observations together, to two clusters. That is the situation that we have considered together that we have seen was able to distinguish quite well between defaulted and non-defaulted clusters. If you consider what happens to the inertia when we move to k equal to 3, 4, 5, and so on, you see that there is actually a decrease as expected. By the way, sometimes you can also see some fluctuations. That depends a lot on the minimization technique that is used within the algorithm, but it's not that important. But you will see that in the long run, you see actually a decrease in the inertia for what concerns the number of classes. Okay, in this plot that you see, it's clear that k is equal to 2. But imagine that instead of just being interested in modeling defaulted and non-defaulted customers, we would be interested in building some sort of warning system, some sort of alarm system, such that, for example, we are able to identify those customers that are maybe close to default, but not yet defaulted, in a way that we may want to contact them to try to understand what is happening and try to avoid that they go default. In that situation, for example, we could be interested in using 3 clusters. So strong defaulted, so strongly defaulted, non-defaulted, and somewhere in between. And using this somewhere in between group to understand using other techniques that we will see together, like, for example, the logistic regression, like, for example, a neural network and whatever, to better understand what is going on. In that situation, if you look at the plot, you see that there is for sure a decrease in the inertia from k equal to 3 with respect to k equal to 2, and for sure k equals to 3 and has a higher inertia with respect to k equal to 4, but we see that if we compare k equal to 2, 3, and 4, probably if we want to build an alarm system, k equal to 3 is the compromise, because the decrease in the inertia between 2 and 3 is definitely higher than the decrease in the inertia between 3 and 4. But again, as I told you, the illusion of having an objective method comes clear because it's just an illusion. At the end of the day, it's up to you to decide what the number of clusters should be. The silhouette method is another method that we can use in order to identify the optimal number of clusters. It can be used as an alternative to the elbow method, but I suggest to use that in addition, because the more methods you use, the better in understanding your data. Now, how does it work? Imagine that we fix the number of clusters. So let's say k equal to 3. Okay? What does it mean? If we fix k equal to 3 and we consider a specific observation I, this observation will belong to one of the clusters and will not belong to the other 2 clusters. Now, what can I do? I take observation I and I compute the distance from observation I to all the other observations in the cluster it belongs to. Then I take the average. This is the quantity Ci that you see in the formula. I then have the other 2 clusters. And what can I do? For the other 2 clusters, for each one of the other 2 clusters, I can compute the distance between my observation I and the observations in that cluster. And I can take the average. So what will happen is that I will obtain 2 averages in our situation. One average represents the average distance between observation I and all the observations in a cluster, and the other would be the average distance between our observation I and all the other observations in the other cluster. Then I take the minimum of these 2 averages. This is the quantity OI that you see in the formula. Now, taking OI minus CI over the maximum between the 2, I obtain a quantity SI that I call silhouette score. Now, the silhouette score necessarily lies between -1 and 1. The higher, so the closer the silhouette score to 1, the better the allocation of our observation to the cluster it belongs to. Why? Because we expect OI to be larger than CI. Why? Because in the opposite situation, it would mean that our observation is closer to observations in the other clusters with respect to the observation in its own cluster. So probably the allocation is not optimal. Now, I can compute CI for every single observation I in my data set, and I can do that for my specific number of k's. So in my example, it was 3. But I can do the same for k equal to 2, k equal to 4, 5, 6, 7. Now, if I compute the silhouette for every single observation given a specific k, I can then take the average of all the silhouette scores for that specific k. And I can build a plot in which on the y-axis I have the average silhouette score, and on the x-axis I have the number of clusters I'm playing with. Now, in this plot, which is the silhouette plot, I will tend to look for the k that maximizes the average silhouette. Now, differently from the elbow method, in this situation, so in the silhouette score, it is quite common to see an erratic behavior. So we can have a value that goes up, down, down, up, and so on. Here, it can be the case that, for example, we have a very large value for k equal to 3, and again, another very large value, even possibly higher, for k equal to 12. Should we prefer necessarily 12 to 3? Here, again, it depends on what you want to do. My suggestion, a very simple heuristic, is always to consider the k that somehow maximizes the average silhouette, but at the same time the lowest k. So it is better to choose k equal to 3 with an average silhouette of 0.65 instead of jumping to k equal to 12 just because the average silhouette there is 0.7. Okay, so there is always this trade-off. It's more or less what happens when you use the archaic criterion. So you always have to look for the value that satisfies the criterion. So for us, that would be maximizing the silhouette score. But there is a trade-off in terms of number of clusters and interpretability of the meaning of the cluster. So always try to understand if it is really better to choose the highest value of silhouette, or it is somehow better to choose a second best, a third best, that, by the way, minimizes the number of clusters. That is, if you have 3 clusters, it's typically easier to give an interpretation of the clusters with respect to having 27 clusters. The last method that we consider together in order to identify the optimal number of clusters is the so-called gaps statistic method, which is based on a very important paper from the early 2000s that introduced actually this statistic. What is interesting of the GAPS method is that it applies to different clustering algorithms. It's not something that just applies, for example, to the k-means. It can be used in other situations. It is a little bit more complicated than the other approaches we have considered because it requires, for example, bootstrapping our data. Now, how does it work? Imagine that we fix a quantity k, so a number k of clusters that we want to obtain, okay? And then our k would be equal to 2, 3, 4, 5. We will do that for different values of k. So, but let's assume that we have fixed k. The first thing that we do is to compute the inertia for that number of cluster k. And this is exactly what we have done before. So we compute the inertia of our algorithm for a given k. After that, we decide a value capital B of bootstrap samples that we want to obtain from our dataset. Typically, B should be larger than 50. But if you go to 100, it's probably even better. So what do? We create capital B bootstrap copies of our original dataset. And for each of these copies, we run the k-means algorithm with the specific k we are considering. After that, I will just take the average over the capital B copies of the log of the inertia for the k-means algorithm applied to every single copy. So for every single copy, every single bootstrap copy, I run my k-means algorithm with the specified k levels. I compute the inertia. I then compute the log of the inertia, the natural logarithm of the inertia. and I take the average of these logs. To the average of these logs, I remove the log of the inertia computed on my original dataset. This is what I called gap for a given k. This is the gap k. Now, for every bootstrap repetition, what can I do? Putting together all my bootstrap samples, I can also compute the standard deviation of the inertia as typical when we bootstrap a quantity. So we can compute the inertia, we can compute the average log inertia, but I can also compute the standard deviation of the log inertia. And I can rescale that quantity that in the formula you see on the screen is SD at level k by the square root of 1 plus 1 over b. This quantity here is what we call Sk. Now, in the gaps method, we look for the value k such that the gap k is larger than equal to gap at level k plus 1 minus sk plus 1, where I repeat, sk plus 1 represents a rescaling of the standard deviation of the log inertia I can compute from my bootstrap copies. Now, what I will have is a plot that against different levels of k will give me this behavior of the gap statistic. And I will choose the value of the k such that this condition of gap k being larger than equal to gap k plus 1 minus sk plus 1, it is satisfied. Here you will see that often for different level of k's, I can get very similar values of the gap statistic. Now, our requirement is that at level k, our gap is larger than equal to. Now, if it is strictly larger, we understand it's not a problem. When it is equal to, then again, here we have that ambiguity that can only be solved by looking at what we need, so at the interpretation that we want to give to the different clusters. But in general, you will always choose the smallest k unless you have some stronger requirements in terms of interpretability. This is the GAPS statistics. As usual, in the description to this video, you will find a link to an R notebook that you can use to replicate the plots I have showed you in this lesson, and you will also find some extra comments. I would like to close this lesson by introducing a topic which is very important in data analysis and that it will appear over and over again in our course, which is the problem of the curse of dimensionality. Now, without being too technical for the moment, the curse of dimensionality is the phenomenon linked to the fact that every time we increase the dimensionality of the problem that we are considering, so for example, we are increasing the dimensions of the data set that we are considering, we are increasing the number of features that we take into consideration in our data set, we are increasing the number of observations in the data set, and we combine this, so we are making things bigger. By making things bigger, for sure, we gain some results, but we also see new problems appearing. So sometimes there is a trade-off, and increasing, for example, the number of covariates does not necessarily improves our interpretability of the phenomenon we are studying. Now, within the k-means algorithm, the curse of dimensionality appears quite clearly when we increase the number of features on which we run the k-means algorithm. Now, we have seen that when we compute the distance between two observations or among the observations in our dataset, we can do that by using just two features, but that can be easily generalized to 3, 4, 5, 6 and number m of features. Now, what we observe, and this is, if you want, a very simple mathematical exercise I leave to you, otherwise believe what I say, is that if you take the Euclidean distance, the average Euclidean distance among the observations in a dataset increases in the number of features. So since these distances are fundamental in the k-means algorithm, the average increase necessarily has an impact on the performances of the algorithm. So increasing the number of features, for example, can make the determination of the clusters a little bit more ambiguous. So it can be more difficult for us to give a clear interpretation of the meaning of the clusters. And it also has an impact in terms of comparability. So it makes no sense to compare the inertia of two different k-means algorithm for the same level k when we have a different number of features. Why? Because the average distance increases, and so the inertia by definition will increase. So that comparability is easily lost. Now, there are solutions that are proposed in the literature, but there is no unique solution. Every time it's some sort of ad hoc solution. A first type of solution is to change the measure of distance that you use. Instead of using, for example, the Euclidean distance, you can use other distances that are rescaled, that is to say, that are forced to be in a specific interval. You can use some measure of correlation that lies between -1 and 1, but you can also use other distances that are rescaled between 0 and 2. So there are different proposals in the literature, and we will consider them in other clustering algorithms, so we will be back. The point is that they are all ad hoceries. There is no unique solution, so the only thing that I can suggest you as, if you want, a heuristical solution is to try to avoid the k-means algorithm when you have a relatively large number of features, and with relatively large, I would say with more than 5 features, it's already quite complicated to give an interpretation, a meaningful interpretation of the clusters, and also to actually clearly distinguish the clusters, because imagine that you are in a 5-dimensional space, so it's a rather complicated object also for us to imagine. So it's always better to play with 2, 3 features. 4 is okay, 5 still acceptable, more it becomes a mess. And by the way, when you have a large number of features, it becomes extremely important to have an idea about the optimal number of k. So the optimal number of clusters you want to obtain. So the k-means algorithm is for sure not the technique you should use when you want to use many features, so you're not able to perform any feature selection, and you want to use all the information, and a lot of information means also a lot of noise. So when you have many features and you don't know how many clusters you will end up with, probably the k-means algorithm is not the best candidate for your analysis. You can use other techniques that we will see together, from hierarchical clustering to other clustering approaches. Okay, so I thank you very much for your attention and see you in the next lesson.